Tonight, we're going to talk about a planet that shouldn't make sense. A world so close to the sun that its surface can melt, lead in daylight. And yet, when the sun disappears, that same world turns into one of the coldest places human eyes have ever measured. Colder than deserts on Mars, colder than moons twice, 3 times, 4 times farther from the sun's light. Closer to the fire than anything else in our solar system, and somehow, unmistakably, freezing. Here's the thing most people don't realize. Distance from the sun feels like it should decide everything. More distance, more cold, less distance, more heat, simple, predictable, safe. But Mercury breaks that rule so completely that scientists spent decades trying to understand how a planet could be both the hottest and the coldest place within reach of our sun, sometimes only hours apart. By the end of tonight, you're going to understand exactly why proximity to a star means almost nothing without something else. Something invisible, something most people forget to ask about when they imagine the planets circling above us in the dark. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. Let's start with the planet itself. Not the mystery yet, just the planet, sitting there in the dark, waiting for you to understand it. Mercury is small, smaller than you might expect. It is the tiniest planet in our solar system, barely larger than our own moon. A quiet grey sphere tucked into the innermost lane of a much larger race. If you lined up all 8 planets side by side, Mercury would almost disappear next to giants like Jupiter or Saturn, and yet despite its size, it holds a kind of record that few people ever think about. It is the closest planet to the sun, the first stop, the nearest neighbour to the star that gives our entire solar system its light and its warmth. Think about what that closeness should mean. If you have ever stood near a fireplace, you know the rule instinctively. Move closer and you feel more heat. Move away and the cold creeps back in. It is one of the simplest, most reliable patterns we learn as children. Distance and temperature, moving together, hand in hand. And for most of the solar system, that rule holds up beautifully. Venus, closer to the sun than Earth, runs hotter than Earth. Mars, farther out, runs colder. Neptune, sitting at the edge of everything, drifts in temperatures so low they barely register as numbers we can imagine. So naturally, you would expect Mercury, the planet closest of all, to be the undisputed champion of heat, the hottest surface, the most relentless sun. A world defined, simply and completely, by scorching temperatures around the clock. Here's the thing most people don't realize. That expectation is only half true. And the other half is where this story really begins. Mercury orbits the sun at a distance of about 36 million miles. Compare that to Earth, which sits roughly 93 million miles away. Mercury is nearly 3 times closer to the sun than we are. At that range, sunlight arrives with a force that is difficult to picture. It is roughly 7 times more intense than what you feel standing outside on a warm, summer day here on Earth. 7 times the light, 7 times the raw solar energy pouring down onto a single, small rocky world. You would think a planet bathed in that much energy could never be anything but blistering. And for half of its surface, at any given moment, that assumption holds. The side of Mercury facing the sun becomes an inferno, a landscape of jagged craters and ancient rock, absorbing energy that has travelled through space for only a few minutes, before slamming into stone that has nowhere to hide. But a planet is not one single place. It is a sphere. It turns. It has a side facing the light and a side facing away from it. And it is that second side, the one turned toward the endless dark, where Mercury quietly begins to break every rule you thought you understood about heat and distance. We are not going to unravel that mystery yet. Not fully. Not tonight. Not in this first quiet stretch of the story. For now, I only want you to hold on to one idea. One small strange fact, tucked away like a secret you will carry with you as we move forward together. Mercury, the planet nearest to the Sun, does not behave the way nearness should predict. Somewhere on its surface, in the hours after sunlight fades, temperatures fall to depths that seem almost impossible for a world sitting this close to a star. Depths that rival, and in some places exceed, the cold recorded on planets, sitting twice, 3 times, even 4 times farther away from that same sun. It is a contradiction, hiding in plain sight. A planet that should be the simplest case study in solar heating, and instead becomes one of the strangest. To understand how this happens, we first need to slow down and really look at Mercury as it exists in space, not as an abstract point on a diagram, but as a real physical world. A place with a surface, a place with a sky, if you could call it that. A place where day and night unfold in ways almost nothing like what you experience here on Earth. Mercury has almost no atmosphere. What little gas surrounds it is so thin, so fragile, that scientists do not even classify it as a true atmosphere in the way we think of Earth's blue sky or the thick orange haze around Venus. Instead, Mercury wears something closer to a whisper of gas, called an exosphere. Individual atoms drift near the surface, occasionally knocked loose by solar wind or micrometeorite impacts, only to escape back into space almost as quickly as they arrived. This detail might seem small right now, almost forgettable, but hold on to it, because this thin, fragile, nearly non-existent layer of gas is going to matter more than almost anything else in tonight's story. It is going to be the quiet, invisible thread connecting everything you learn about this strange little planet. Mercury also moves differently than you might expect. It completes one full orbit around the Sun in just 88 Earth days. A year on Mercury flashes by in less than 3 months of our time, and yet its rotation, the way it spins on its own axis, is slow. Strangely, almost hypnotically slow. So slow that a single day and night cycle on Mercury, from sunrise to sunrise, actually lasts longer than its entire year. Sit with that for a moment. A planet where the day is longer than the year. A planet that finishes an entire trip around the Sun before it even finishes turning once from light into darkness and back into light again. This is not a normal world. This is not a simple, predictable rock following the rules you learned as a child, standing near a fire, feeling the heat fade as you step away. This is a planet built on contradictions, blazing and frozen, close and somehow impossibly cold, fast around the Sun, yet slow to turn beneath it. And it is precisely this collection of contradictions, this quiet accumulation of strange facts, that sets the stage for everything still ahead. Because to understand why Mercury runs colder at night than worlds twice as far from the Sun, we cannot simply look at distance. We have to look at everything else, the thin whisper of gas surrounding it, the long, slow turning of its axis, the invisible physics governing how heat arrives, how it lingers, and how it disappears. For now, let this be enough. A small planet, the closest to the Sun, and already, in these first quiet details, the first threads of a mystery beginning to unravel in the dark. So let's stay with the daylight side for a while longer, because before we can understand the cold, you need to feel the full weight of the heat, not just as a number, but as something almost physical, something you can picture pressing down on bare rock, hour after hour, with nothing to soften it. When the Sun rises over Mercury's cratered surface, it does not rise gently. There is no soft dawn, no gradual warming of the air, no birds beginning to stir in the early light. There is no air at all to carry any of that. Instead, sunlight arrives instantly and directly, striking bare stone with a force that would be unbearable to any living thing standing there. Within hours, temperatures on the sun-facing side climb past levels that are difficult to compare to anything in ordinary human experience. At its hottest, Mercury's daytime surface can reach around 800 degrees Fahrenheit. In terms most of us can picture more easily, that means the ground itself becomes hot enough to melt lead. not warm it, not soften it, melt it completely, turning solid metal into liquid on contact with the surface. Try to imagine standing on ground that could dissolve metal beneath your feet, and you begin to understand what daylight truly means on this planet. And this heat is not isolated to some rare, unusual location. It spreads across the entire hemisphere facing the sun. Craters, plains, ancient impact basins, all of it baked under the same relentless light, hour after hour, for weeks at a time. Because remember, a single day on Mercury lasts far longer than a day on Earth. That blistering heat is not something that arrives and fades within hours. It lingers, builds, and intensifies, with no clouds, no wind, no atmosphere of any kind to interrupt it. Here's the thing most people don't realize: Mercury is not always the same distance from the Sun. Its orbit is not a perfect circle. It stretches into more of an oval shape, which means that at certain points, Mercury swings even closer to the Sun than usual. Scientists call this closest point perihelion, and when Mercury reaches it, the intensity of sunlight striking its surface climbs even higher than the numbers we just described. The planet essentially leans into the fire, drawing nearer to the very source of all that heat. At this closest distance, sunlight becomes more than 10 times more intense than what reaches Earth on an ordinary day. 10 times the light, 10 times the raw solar energy pouring onto a surface with nothing to shield it, nothing to scatter it, nothing to soften its impact. If you have ever felt the sting of sunlight on your skin during a bright afternoon, multiply that sensation by 10, and you begin to approach what Mercury experiences at its most extreme. Compare this now to Venus, a planet many people mistakenly assume must be hotter, simply because its thick atmosphere traps so much heat so effectively. And it is true that Venus holds the title for the highest average surface temperature of any planet in our solar system, warmed relentlessly by a runaway greenhouse effect. But in terms of raw daytime peak heat, driven purely by direct exposure to the sun, Mercury's blazing hemisphere can rival even Venus in isolated moments. Two very different planets, reaching similarly staggering extremes through two very different mechanisms. This is where it becomes tempting to draw a simple conclusion. Mercury sits closest to the sun. Mercury receives the most intense sunlight. Therefore, Mercury should logically be, in every sense, the hottest world in our solar system. A planet defined entirely by fire day and night, without exception. And if you only ever looked at the numbers we've covered so far, that conclusion would feel completely reasonable. The proximity is real. The intensity of sunlight is real. The temperatures capable of melting metal are real, measured, and confirmed by spacecraft that have studied this planet up close. Everything you've heard tonight so far supports a single, simple story. Closeness equals heat. Heat defines Mercury, but a planet is never defined by only half of its surface, and it is never defined by only half of its story. Even as that daylight side bakes under conditions capable of melting lead, something entirely different is unfolding on the other side of this small spinning world. A side turned away from the sun, a side where all of that intense energy simply cannot reach. And it is there, in that hidden hemisphere, where the true nature of Mercury begins to reveal itself. We are not ready to step into that darkness quite yet. For now, I want you to sit with the full weight of what daylight truly means on this planet. The scale of it, the intensity of it, the almost unimaginable violence of sunlight, unfiltered by any atmosphere, striking bare stone again and again, for hour after hour, day after impossibly long day. Because only once you understand exactly how hot Mercury becomes under direct sunlight can you begin to appreciate just how strange, just how contradictory, what happens next truly is. A planet capable of melting metal in daylight, and yet, only hours later, capable of temperatures that plunge to depths rivaling the coldest, most distant corners of our solar system. This is the seat closest to the fire, the nearest planet to a star that gives light and warmth to everything orbiting around it. And soon, you will understand why sitting closest to that fire does not guarantee warmth at all. Not everywhere. Not always. Not on a world like this one. To understand what happens on the far side of Mercury, we need to talk about something you already know intimately, even if you've never thought about it in these terms. We need to talk about blankets. Not literal ones, not the kind you might be wrapped in right now as you listen to this, but the invisible kind. The kind that every planet either has or doesn't have, wrapped around it in the vacuum of space. Think about a cold night here on Earth. If you step outside without a coat, you feel the chill almost immediately. But wrap yourself in a heavy blanket, and something remarkable happens. Your own body heat, the warmth you generate simply by being alive, gets trapped close to your skin. It doesn't escape into the cold air around you. It lingers, it accumulates, it keeps you warm long after the source of that heat would otherwise have drifted away into the night. This is not really about the blanket producing warmth at all. It is about the blanket preventing warmth from leaving. Every planet with a meaningful atmosphere experiences something remarkably similar. Gas molecules surrounding a planet act like that blanket, catching heat that would otherwise radiate straight back out into the emptiness of space. They trap it, they circulate it, they hold on to it, even after the sun has set and darkness has fallen. This is precisely why Earth's nights, even in winter, rarely plunge to anything close to the extremes found elsewhere in our solar system. Our atmosphere, thin as it seems when you look up at a clear blue sky, is doing enormous, quiet work every single moment, retaining warmth that would otherwise vanish. Now return with me to Mercury. Recall that thin, fragile detail from earlier, that whisper of gas surrounding this small planet, so sparse that scientists hesitate to even call it an atmosphere at all. An exosphere, made of scattered atoms, drifting and escaping almost as quickly as they arrive. This is Mercury's blanket. Or rather, this is the almost complete absence of one. Here's the thing most people don't realise. It is not the sun's heat itself that determines how warm a planet stays. It is what that planet does with the heat once it arrives. A star can pour enormous amounts of energy onto a surface, but if there is nothing there to hold on to that energy, to trap it, to slow its escape back into space, then all of that heat simply radiates away again, sometimes remarkably quickly. Mercury receives immense sunlight, more intense than almost anywhere else in our solar system, but it has virtually nothing to keep that heat once the sun disappears from the sky. Picture it this way. Imagine standing beside a campfire on a clear, windless night. As long as you stand close to the flames, you feel intense heat radiating against your skin. But the moment you step just a few feet away into open darkness, that warmth disappears almost instantly. There is no surrounding layer of warm air holding onto that heat for you, no blanket of insulation keeping the warmth lingering nearby. The heat simply radiates outward and vanishes into the cold night air surrounding you. Mercury experiences something remarkably similar, but on a planetary scale and with far more extreme consequences. During the day, sunlight strikes the surface directly, heating rock and dust to extraordinary temperatures. But there is no atmosphere circulating that heat, redistributing it, holding it close to the surface after sunset. The moment the sun disappears below Mercury's horizon, the surface begins losing heat almost immediately, radiating that stored energy straight back out into the vacuum of space, with nothing at all standing in its way. This single missing ingredient, this thin, nearly non-existent layer of gas, turns out to be one of the most important details in our entire story tonight. Without it, Mercury cannot hold on to the heat it receives. Without it, daytime warmth has no way of lingering into the night. Without it, the connection between sunlight and surface temperature becomes far less predictable, far less simple than most people assume when they first imagine this small planet closest to our Sun. And this absence explains something crucial about why proximity to the Sun does not automatically translate into consistent warmth. A planet's true temperature, especially after sunset, depends heavily on its ability to retain heat, not merely on how much heat it initially receives. Mercury receives an enormous, overwhelming amount of solar energy, but almost none of it stays. Think back to that image of standing without a coat on a cold night. Now imagine standing there for hours, then suddenly stepping into blistering summer heat, then stepping straight back into that same freezing night again, over and over, with nothing gradual about the transition. No twilight easing you from one extreme into the other, no lingering warmth carrying over from daylight hours, just an abrupt, immediate shift from one extreme condition to its complete opposite. This is beginning to explain the contradiction we introduced earlier. A planet so close to the Sun that it can melt lead under direct sunlight. And yet, once that sunlight disappears, a planet with almost nothing standing between its surface and the endless cold of space. The proximity to the Sun determines how intense the daytime heat becomes, but the almost complete absence of atmosphere determines how quickly and how completely that heat disappears once night falls. We're getting closer now to understanding the true mechanics behind Mercury's strange and contradictory nature. But there is still more to uncover, because knowing that Mercury lacks a meaningful atmosphere tells us why heat escapes so easily. It does not yet tell us exactly how cold things truly become once that heat is gone, or how Mercury's own unusual rotation extends and deepens that darkness far beyond what you might expect from an ordinary planetary night. Let's stay a little longer on the sunlit side of Mercury, because there is something here that most people never think to ask about. Something buried just beneath the surface, hidden under all that visible heat, and it is going to matter more than you might expect when we finally step into the darkness later tonight. If you could somehow stand on Mercury's daylight side, protected from the heat and the radiation, the first thing you would notice is the sky. Even at high noon, with the sun blazing directly overhead, the sky above you would remain completely black. Not blue, not hazy, just an endless, star-filled darkness stretching in every direction. Because there is no atmosphere present to scatter light the way it does here on Earth, the sun itself would appear enormous, several times larger than it looks from our own planet. A blinding white disk burning against a backdrop of total night. This alone tells you something important about how strange daylight truly is on this world. There is no soft blue sky to soften the intensity of the sun, no gentle diffusion of light across the horizon, just raw, direct, unfiltered energy striking bare rock, with nothing standing between the source and the surface. Every bit of heat that reaches Mercury arrives with full undiluted force, concentrated entirely on whatever ground happens to be facing the sun in that moment. Now, here is the detail that surprises almost everyone who studies this planet closely. Despite the extraordinary heat scorching the surface, that heat does not travel far downward. If you were to dig just a few inches beneath Mercury's blistering hot ground, even in the middle of the hottest part of the day, the temperature would drop dramatically. Not gradually, dramatically. Within a shallow layer of loose, dusty material called regolith, heat simply fails to penetrate very deep at all. This happens because Mercury's surface material behaves almost like an insulator, similar in some ways to how a thick layer of ash might protect the ground beneath it from an intense fire burning above. The loose, powdery regolith covering much of Mercury's surface does not conduct heat efficiently downward. So even while temperatures at the very top layer soar high enough to melt lead, temperatures only a short distance below remain far cooler, almost shockingly so, compared to the inferno raging just above them. Here's the thing most people don't realize. This means Mercury is not simply hot all the way through, baked uniformly from surface to core by its closeness to the sun. It is hot in a thin, almost superficial layer, while remaining remarkably insulated just beneath that surface. Heat here behaves less like an even spreading warmth, and more like a sheet of fire sitting directly on top of something far colder, with almost no blending between the two. This detail becomes especially important when we consider certain hidden regions of Mercury that we will explore later tonight, places where sunlight never reaches at all, and where this insulating quality of the surface plays a critical role in preserving cold in ways that might otherwise seem impossible, so close to the sun. For now, simply notice this quiet contradiction sitting right at the heart of daylight itself. Blistering heat above, cooler stillness only inches below. Think for a moment about how different this is from what you experience here on Earth. When sunlight warms the ground beneath your feet on a hot summer day, that warmth spreads gradually downward and outward, carried by air, moisture, and the physical properties of soil and rock that conduct heat far more efficiently. Mercury lacks nearly all of these mechanisms. There is no air to help distribute warmth, no moisture to retain or transfer it evenly. Only bare regolith, sunlight, and vacuum interacting in ways that produce far sharper, far more localized extremes than anything familiar to us. And this pattern, this tendency towards sudden extremes rather than gradual transitions, reflects something essential about Mercury as a whole. This is not a planet built on gentle gradients or smooth transitions between conditions. It is a world defined by abrupt boundaries, blazing surfaces beside cooler ground just inches away, daylight capable of melting metal, existing only steps from permanent shadow that has perhaps never felt warmth at all. As the hours pass and Mercury's slow rotation gradually carries a given point on its surface, away from direct sunlight, all of that intense heat accumulated across the daylight hours faces a serious problem. With no atmosphere circulating it, no insulating blanket holding it in place, and a surface that barely conducts heat downward in the first place, that stored warmth has essentially nowhere to go except straight back out into space. And it does so remarkably quickly once sunlight disappears entirely. We are approaching the edge now. The daylight hours, with all their scorching intensity, are beginning to end. And on the other side of that boundary waits something else entirely. A transition unlike anything most of us have ever experienced. A shift so extreme, so immediate that it becomes difficult to believe both conditions exist on the very same small, quiet world, spinning patiently around the same sun that governs every planet in our story tonight. Now let's cross that boundary together. Let's follow a single patch of ground on Mercury's surface as it slowly turns away from the sun, carrying with it hours of accumulated heat. And watch what happens next. As the sun sinks toward the horizon on Mercury, there is no long, gentle twilight the way we experience here on Earth. There is no golden hour, no soft fading of light across the sky, no gradual cooling that eases the transition from day into night, because there is no atmosphere to scatter light or bend it around the curve of the planet. Sunset here happens with startling abruptness. One moment, the sun sits visible above the horizon, blazing and enormous. The next, it drops away almost entirely, and true darkness begins to settle in with very little warning. The moment sunlight disappears from a given patch of Mercury's surface, that surface begins losing heat almost instantly. Remember, there is no insulating blanket of gas here to slow that process down. No warm air lingering nearby to hold on to the day's accumulated energy. Every bit of stored heat radiates directly back out into the vacuum of space, escaping far more quickly than it ever could on a planet with even a thin, functioning atmosphere. Within a surprisingly short period of time, temperatures that once soared high enough to melt lead begin plunging toward levels that seem almost unbelievable. Here's the thing most people don't realize. This is not a gradual cooling stretched out gently over many hours. It is closer to a collapse, a rapid, dramatic drop from one extreme condition to its complete opposite, happening within a relatively short window of time once night finally arrives. Scientists studying Mercury have recorded nighttime surface temperatures plunging to around -290 degrees Fahrenheit, a cold so extreme it becomes difficult for most of us to translate into anything resembling lived experience. Try to imagine it this way. Picture the hottest day you have ever experienced, standing directly in blazing summer sunlight with sweat forming on your skin within minutes. Now imagine, within the span of just a few hours, being transported into cold so severe that it exists closer to the temperatures found in deep space itself than anything you have ever felt standing outside on even the harshest winter night here on Earth. That is the scale of transition happening on Mercury over and over in every single day and night cycle. This abrupt, violent temperature swing raises an obvious and unsettling question. If Mercury is genuinely this close to the Sun, if it receives sunlight intense enough to melt metal during the day, how can it possibly plunge to such extraordinary cold once that sunlight disappears? Shouldn't a planet this close to its star retain at least some residual warmth, some lingering heat carried over from daylight hours, easing the transition into night rather than allowing such an extreme and immediate collapse? And this is precisely where Mercury begins revealing something deeply important about how temperature actually works across our solar system. Proximity to the Sun determines how intense sunlight becomes when it strikes the surface directly, but it does not by itself determine how warm that surface remains once sunlight disappears. That second question depends entirely on a planet's ability to trap and retain heat, something Mercury simply does not have the tools to accomplish. Without an atmosphere circulating warmth, without gases capable of holding on to stored energy, without any meaningful blanket wrapped around this small planet, heat generated during the day has virtually no way of surviving the transition into night. It escapes almost as quickly as it arrived, radiating outward into space with startling efficiency, leaving behind a surface that cools far more dramatically, far more completely than most people would ever expect from a world sitting this close to a star. Think back again to that image of standing beside a campfire on a clear, windless night. The moment you step away from those flames, warmth disappears almost instantly, because there is nothing nearby holding on to it for you. Mercury experiences something remarkably similar, but stretched across an entire planetary surface, and intensified by the complete absence of any atmosphere whatsoever. The moment sunlight moves elsewhere, warmth vanishes almost immediately, leaving behind conditions closer to the depths of interstellar space than anything resembling the daytime inferno that existed only hours before. And this is only the beginning of the story behind Mercury's extraordinary cold, because the darkness that follows sunset here does not simply linger for a typical night, the way it might on Earth, fading again within a matter of hours before sunrise returns warmth once more. On Mercury, once darkness falls, it settles in for an extraordinarily long time, far longer than most people ever imagine when they first picture a single day passing on another planet. We are only just beginning to understand why these nights run so cold. Soon we will explore exactly how long that darkness truly lasts, and why Mercury's strange, unusual rotation plays such a critical role in deepening this cold far beyond what a simple sunset alone could ever explain. Let's go deeper now into that strange detail we touched on earlier. The idea that a single day on Mercury outlasts its entire year, because understanding exactly why this happens and exactly how long that darkness truly stretches is essential to understanding why Mercury's nights become so brutally cold. Mercury spins on its axis far more slowly than Earth does. While our planet completes a full rotation roughly every 24 hours, Mercury takes approximately 59 Earth days just to turn once on its axis. That alone would be remarkable enough, a planet turning so slowly that a single rotation stretches across nearly 2 of our months. But the truly strange part comes from combining this slow spin with Mercury's rapid orbit around the Sun, a journey it completes in only 88 Earth days. Here's the thing most people don't realise. Because of the particular way Mercury's rotation and orbit interact with one another, a single full day and night cycle, from one sunrise to the next, actually takes about 176 Earth days to complete. That means, from the perspective of someone standing on Mercury's surface, waiting for the sun to rise again after it sets, they would need to wait roughly 2 entire Mercury years before that sunrise finally arrived. Scientists describe this unusual relationship using something called a 3-to-2 spin orbit resonance. In simple terms, for every 2 complete trips Mercury makes around the Sun, it rotates exactly 3 times on its own axis. This precise, almost musical relationship between orbit and rotation did not happen by accident. It developed gradually over billions of years, shaped by the powerful gravitational pull of the Sun acting on Mercury's slightly irregular shape, gradually locking its rotation into this strange, stable rhythm. Try to picture what this actually means for a single point on Mercury's surface. Sunrise arrives, and daylight begins, stretching on for the equivalent of 88 Earth days before the Sun finally begins sinking toward the horizon again. Then, once darkness falls, that same point on the surface remains in shadow for another 88 Earth days before sunlight finally returns. 2 entire Earth months of blazing daylight, followed by 2 entire Earth months of uninterrupted darkness, repeating in this same extraordinary rhythm, over and over, throughout Mercury's existence. Now think back to everything we explored about how quickly heat escapes once sunlight disappears from Mercury's surface. With no atmosphere to retain warmth, temperatures begin plunging almost immediately after sunset. And on Earth, that cooling process gets interrupted relatively quickly, because our nights last only a matter of hours before sunlight returns and begins warming the surface once again. But on Mercury, there is no such interruption. That cooling process continues, uninterrupted, for the equivalent of nearly 3 full Earth months. This extended darkness gives Mercury's surface an enormous amount of time to radiate away every last trace of stored heat, far more time than almost any other planet's night cycle allows. It is not simply that Mercury cools quickly once the sun sets, though that is certainly part of the story. It is that this cooling process then continues, essentially unopposed, for an extraordinarily long stretch of time, allowing temperatures to plunge to depths that a shorter night could never achieve. Imagine, for a moment, leaving a warm object outside on a cold evening here on Earth. Within a few hours, it will have lost a significant portion of its heat, cooling steadily toward the surrounding temperature of the night air. Now imagine leaving that same object outside, exposed to that same cold. Not for a few hours, but for nearly 3 uninterrupted months, with absolutely nothing to slow the process or reintroduce warmth along the way. The eventual temperature you would reach becomes almost impossible to compare to anything most of us have directly experienced. This is precisely what happens across Mercury's night side, over and over, throughout every single orbit around the Sun. And it helps explain, at least in part, why nighttime temperatures here can plunge so dramatically lower than what we might expect from a planet sitting so remarkably close to our Sun. The proximity to the Sun determines how intense daylight becomes. The absence of atmosphere determines how quickly heat escapes once night falls. And this extraordinarily long night, stretched across nearly 3 Earth months, determines just how deep that cold is ultimately allowed to become before sunlight finally interrupts it again. But even this extraordinary combination, slow rotation, rapid orbit, thin atmosphere, and extended darkness, does not yet reveal the coldest places found anywhere on Mercury's surface. Because there exist certain regions on this small contradictory planet where the sun never rises at all. Not once, not ever. Places locked in permanent shadow, hidden just miles from some of the hottest terrain found anywhere in our solar system. And it is there, in that permanent darkness, where Mercury's true extremes finally reveal themselves completely. Now we arrive at something truly strange, something that sounds almost like a contradiction wrapped inside a contradiction. Because on a planet already famous for its blazing daylight and its brutal extended nights, there exist places that experience neither one. Places where the sun, in a very real and literal sense, never rises at all. Mercury's axis of rotation is tilted only slightly, almost perfectly upright, compared to its orbital path around the sun. This might sound like a minor technical detail, but it produces a remarkable consequence near the planet's north and south poles. Because Mercury barely tilts at all, sunlight there approaches at an extremely shallow angle, skimming almost horizontally across the landscape, rather than shining down directly from above. And within certain deep craters near these poles, that shallow sunlight simply cannot reach the crater floor at all. Here's the thing most people don't realize. These polar craters are so deep, and the surrounding crater walls so tall, that they cast permanent shadows across their interior floors. Shadows that never move, shadows that never shrink, shadows that have likely existed, unbroken and unchanging, for billions of years. Regions locked inside these craters have quite possibly never experienced a single moment of direct sunlight since the earliest days of our solar system's formation. Try to picture that scale of permanence. Every single day for as long as this planet has existed, spinning around the same star that scorches its equator with heat capable of melting metal, and yet certain small pockets near its poles have remained in absolute, unbroken darkness the entire time. Not because night eventually falls there, the way it does everywhere else on Mercury, but because the geometry of these craters, combined with Mercury's nearly upright tilt, makes sunlight physically incapable of ever reaching their depths. And this permanent shadow produces consequences that go far beyond anything we have discussed so far. Without sunlight ever reaching these crater floors, even briefly, even for a single moment across billions of years, temperatures inside these permanently shadowed regions plunge to levels that rival some of the coldest measured temperatures anywhere in our entire solar system. Scientists studying data from spacecraft instruments estimate that conditions inside these craters can drop to around negative 370 degrees Fahrenheit, a cold so extreme that it approaches temperatures found only in the depths of interstellar space itself. Think about the scale of what that number actually represents. Compare it to the coldest recorded temperature ever measured naturally here on Earth, in the most remote frozen stretches of Antarctica, hovering somewhere around negative 128 degrees Fahrenheit. Mercury's permanently shadowed craters run colder than that by an almost unimaginable margin, nearly 3 times colder than the harshest cold our own planet has ever produced. And remember exactly where these craters are located. Not on some distant frozen world far removed from our sun, not tucked away in the outer reaches of the solar system, where sunlight naturally grows weak and diffuse over enormous distances. These craters sit on Mercury, the closest planet to the sun, a world where, only a short distance away, temperatures on the sunlit equator soar high enough to melt lead completely. This is precisely the kind of contradiction that makes Mercury so difficult to categorize using simple, familiar assumptions about heat and distance. On the very same planet, within a relatively short distance of one another, you can find surface conditions hot enough to liquefy metal, and surface conditions colder than almost anywhere else measured across our entire solar system. Not 2 different planets, not 2 vastly different distances from the sun. The very same small world, holding both extremes simultaneously, separated by nothing more than the presence or absence of direct sunlight. This detail forces us to reconsider everything we thought we understood at the beginning of tonight's journey. Distance from the sun clearly matters. It determines how intense sunlight becomes when it does strike a surface. But as we're discovering, distance alone cannot explain everything happening on a planet's surface. Geography matters. The angle of sunlight matters. The presence or complete absence of any atmosphere capable of redistributing warmth matters enormously. And on Mercury, these factors combine to produce a planet capable of extremes that defy simple, straightforward explanation. But this permanent, ancient cold hiding within Mercury's polar shadows raises another question, one that scientists themselves did not expect to encounter when they first began studying this small scorched planet up close. Because extreme cold, sustained over billions of years in complete darkness, creates exactly the right conditions for something almost nobody expected to survive anywhere near the sun's closest neighbour. Something that seems, at first glance, almost impossible to imagine existing on a planet defined by fire and heat. We are about to discover exactly what that something is. In the 1990s, astronomers pointed powerful radar systems from Earth toward Mercury, hoping to map details of its surface that ordinary telescopes could never resolve clearly from such a great distance. What they found, reflected back from those permanently shadowed craters near Mercury's poles, was not what anyone expected. Bright, highly reflective patches appeared in the radar data, patches with signatures remarkably similar to something scientists knew well from studying icy moons and comets elsewhere in our solar system. Water ice. At first, this seemed almost impossible to believe. Mercury, the planet sitting closest to the sun, the world capable of melting lead under direct sunlight, appeared to be hiding frozen water within craters near its poles. It sounded like a contradiction, too strange to be true, the kind of detail that seems more suited to a distant, frozen world at the outer edges of our solar system than to the sun's nearest neighbour. And yet the radar signatures persisted, consistent and unmistakable, appearing precisely within those regions locked in permanent shadow. Here's the thing most people don't realise. Confirmation eventually came directly from a spacecraft, one that had travelled all the way to Mercury specifically to study this small, extreme planet up close. Named Messenger, this spacecraft entered orbit around Mercury and spent years gathering detailed data about its surface, its subtle magnetic field, and yes, those mysterious bright patches hidden within polar craters. Using instruments capable of detecting hydrogen and mapping surface reflectivity with remarkable precision, Messenger confirmed what radar observations had long suggested. Water ice truly does exist within Mercury's permanently shadowed polar craters. Try to sit with the strangeness of that discovery for a moment. On a planet where daytime temperatures soar high enough to liquefy metal, frozen water sits patiently within hidden craters, protected from every trace of direct sunlight by walls of ancient rock. Two conditions that feel like they belong to entirely separate worlds, coexisting quietly on the very same small planet, separated by nothing more than a difference in elevation and angle, and a shadow that has never once been broken by light. Scientists estimate that these icy deposits, though modest compared to something like Earth's polar ice caps, still represent a meaningful and measurable amount of frozen water, potentially enough to fill a moderately sized lake if it were ever somehow gathered together and melted. This ice likely arrived on Mercury the same way water arrived on many rocky worlds throughout our solar system's early history, delivered by comets and certain types of asteroids that struck the planet's surface across billions of years, leaving behind trace amounts of water that eventually found their way into these permanently frozen sanctuaries near the poles. And here we encounter one of the most genuinely shocking aspects of tonight's entire story. This ice has likely persisted, undisturbed and unmelted, for potentially billions of years. While the rest of Mercury endured relentless bombardment from intense sunlight, scorching temperatures capable of transforming solid metal into liquid, these small isolated pockets remained perfectly preserved, locked away in permanent cold and permanent darkness, completely untouched by the extremes defining almost every other part of this planet's surface. This discovery forces us to reconsider, once again, everything we thought we understood about this small contradictory world. Mercury is not simply a planet of fire, defined entirely by its closeness to the Sun and the extraordinary heat that closeness produces. It is also, quietly and almost secretly, a planet capable of preserving ice for timescales stretching back to the earliest chapters of our solar system's history. Fire and ice existing simultaneously on the very same small rocky world. Think about what this means for how we understand the relationship between distance and temperature across our entire solar system. If frozen water can survive, protected and preserved, on the planet closest to the Sun, then clearly proximity alone tells us far less than we initially assumed. What matters, again and again throughout tonight's story, is not simply how far a world sits from its star, but the specific, local conditions shaping every individual region across that world's surface. Shadow, geography, the angle of sunlight, the presence or absence of atmosphere. All of these details matter enormously, sometimes far more than distance itself. And this growing realization brings us naturally to a broader comparison, one that will help clarify exactly why Mercury behaves so differently from other planets in our solar system, despite sitting closest to the very source of all that light and warmth. Because if proximity alone determined temperature, planets sitting farther from the Sun should always run predictably colder than Mercury, with no exceptions and no contradictions of their own. But as we are about to discover, that simple assumption breaks down almost immediately once we begin examining our neighbouring worlds more closely. Let's travel outward now, away from Mercury, toward a planet most people already think they understand fairly well. Mars, the red planet, a world roughly 1.5 times farther from the Sun than Earth, and more than twice as far from the Sun as Mercury. If distance alone determined temperature, Mars should be dramatically, unquestionably colder than Mercury in every possible way, at every hour of its day and night. And in many respects, that assumption holds up perfectly well. Mars is, on average, a genuinely frigid world. Its thin atmosphere, composed mostly of carbon dioxide, provides only a fraction of the insulating power that Earth's atmosphere offers, leaving average temperatures across the planet hovering around -80 degrees Fahrenheit. During Martian winters, especially near the poles, temperatures can plunge even further, sometimes low enough to freeze carbon dioxide directly out of the atmosphere, forming delicate frost across the frozen ground. By almost any measure, Mars stands as a bitterly cold world, consistent with its greater distance from the Sun. Here's the thing most people don't realise. Despite sitting so much farther from the Sun, Mars actually retains a meaningfully thin atmosphere, unlike Mercury's almost non-existent exosphere. This atmosphere, while far too thin to trap heat as effectively as Earth's does, still provides just enough insulation to prevent the kind of violent, extreme temperature swings that define Mercury's day and night cycle. Nighttime temperatures on Mars do drop significantly compared to daytime highs, but nowhere near as dramatically and nowhere near as suddenly as what happens across Mercury's surface once the Sun disappears. Consider a specific direct comparison. On a relatively mild day near the Martian equator, daytime temperatures can occasionally climb to something surprisingly close to a comfortable spring afternoon here on Earth, sometimes reaching slightly above the freezing point of water. Yet even after the Sun sets, thanks to that thin but present atmosphere, circulating some residual warmth, Martian nighttime temperatures in these regions might only drop to somewhere around -100 degrees Fahrenheit. Extremely cold, certainly, by any human standard, but nowhere close to Mercury's plunge toward -290 degrees Fahrenheit across much of its surface, or the even more extreme -370 degrees Fahrenheit found within its permanently shadowed polar craters. Think about what this comparison actually reveals. Mars, sitting more than twice as far from the Sun as Mercury, experiences less extreme nighttime cold in many of its equatorial regions than Mercury does across large portions of its own surface. A planet farther from the Sun, in this particular respect, staying meaningfully warmer at night than a planet sitting dramatically closer to that same star. This is precisely the contradiction we promised to explain at the very beginning of tonight's journey together. And the explanation, as we've been building toward throughout this entire story, comes down almost entirely to atmosphere. Mars's atmosphere, though far thinner than Earth's, still provides enough insulating capability to trap a meaningful portion of the heat absorbed during daylight hours, releasing it slowly overnight rather than allowing it to escape instantly and completely into space. Mercury, lacking any comparable atmosphere at all, has no such mechanism available. Heat absorbed during its long daylight hours simply radiates away almost entirely, with virtually nothing standing in its way. This single difference, the presence of even a thin atmosphere versus its near-total absence, explains far more about a planet's nighttime temperature than distance from the Sun ever could on its own. Mars proves this beautifully, almost as though nature designed the perfect experiment specifically to illustrate this exact point. Two planets, vastly different distances from the Sun, and yet nighttime cold behaving in ways that directly contradict what simple distance alone would ever predict. Of course, Mars still runs colder than Mercury on average, when accounting for the planet's overall temperature across its entire orbit and its more distant position from the Sun's warmth. This comparison is not suggesting that Mars is somehow a warmer planet than Mercury in every conceivable sense. Rather, it reveals something more precise and more important. When it comes specifically to nighttime cold, to how dramatically temperatures fall once sunlight disappears, atmosphere matters more than distance. Insulation matters more than proximity. And Mercury's almost complete absence of atmosphere allows its nights to plunge to depths that even a much more distant, thinly atmosphered world like Mars simply does not experience in its milder regions. This pattern becomes even clearer, even more striking, when we turn our attention toward a planet with a genuinely thick, powerful atmosphere. A planet close enough to home that you have likely felt its protective effects yourself, every single day of your life, without ever fully appreciating just how much work that atmosphere performs to keep your own nights so much gentler than anything experienced across Mercury's cratered, contradictory surface. Let's bring this comparison closer to home now, closer than Mars, closer than Mercury. Let's talk about the planet you're standing on, or lying on right now, as you listen to this in the dark. Earth sits roughly 93 million miles from the Sun, nearly 3 times farther away than Mercury. If proximity alone determined temperature, our nights should be bitterly cold. Perhaps not quite as extreme as Mercury's, but certainly far colder than most of us ever actually experience. And yet, even in the depths of winter, in the coldest regions of our planet, nighttime temperatures rarely approach anything close to what Mercury experiences after even a single ordinary sunset. This is not luck. This is not simply a matter of Earth receiving some perfectly moderate amount of sunlight. This is the direct result of something Mercury almost entirely lacks: a thick, dynamic, remarkably effective atmosphere. Here's the thing most people don't realize: Earth's atmosphere does far more than simply provide air to breathe. It acts as an enormous, planet-wide insulating layer, composed of nitrogen, oxygen, and smaller amounts of other gases, including carbon dioxide and water vapour, that together trap a significant portion of the heat absorbed from the sun during daylight hours. This trapped heat does not disappear the moment the sun sets. Instead, it lingers, circulating through the atmosphere, radiating slowly back toward the surface, keeping nighttime temperatures far gentler than they would ever be on a planet without this protective layer. Scientists refer to this process as the greenhouse effect, though the version occurring naturally on Earth operates in a careful, balanced way that has allowed life to flourish for billions of years. Certain gases in our atmosphere, particularly water vapour and carbon dioxide, absorb infrared radiation, essentially heat energy, as it attempts to escape back into space after sunset. Rather than allowing that heat to radiate away instantly and completely, the way it does on Mercury, these gases capture a portion of it and redirect some of that energy back toward the surface, creating a kind of continuous gentle recycling of warmth throughout the night. Think about what this means in very practical terms. Without this atmospheric blanket, Earth's average global temperature would sit dramatically lower than it does today, potentially plunging to levels closer to freezing across the entire planet, even during daylight hours. Our atmosphere does not simply moderate temperature swings between day and night. It fundamentally makes the kind of stable, livable conditions we take for granted possible in the first place. Every comfortable night you have ever slept through, every gentle evening breeze you have ever felt, exists because of this invisible, enormous, endlessly working layer of gas surrounding our entire planet. Compare this now directly to Mercury, sitting nearly 3 times closer to the Sun, yet possessing none of this atmospheric protection. Mercury receives far more intense sunlight than Earth ever does, and yet, because it lacks any meaningful atmosphere capable of trapping and redistributing that heat, its nighttime temperatures plunge to depths that would be utterly catastrophic and completely unsurvivable for anything resembling life as we understand it. Meanwhile, Earth, despite sitting so much farther from that same sun, maintains temperatures gentle enough to support oceans, forests, and every living creature that calls this planet home. This comparison reveals, with striking clarity, the true lesson buried at the heart of tonight's entire story. Distance from the sun determines how much raw solar energy a planet initially receives. But atmosphere, its presence, its thickness, its specific chemical composition, determines what actually happens to that energy once it arrives, whether it lingers gently, warming a planet's surface through day and night alike, or whether it escapes almost instantly, leaving behind the kind of violent extremes we've explored across Mercury's tormented, contradictory landscape. And this realization carries an emotional weight that extends far beyond simple planetary science. Earth's atmosphere, this thin, fragile, easily overlooked layer of gas surrounding our entire world, is not some minor detail incidental to our comfort. It is the single most important factor separating our gentle, livable nights from something closer to the brutal extremes experienced across much of Mercury's surface. We rarely think about the atmosphere as we go about our daily lives, rarely pause to appreciate its constant, quiet work protecting us from the harsher realities of space. And yet without it, none of the comfort, none of the stability, none of the life we take entirely for granted could exist at all. Understanding this comparison between Mercury, Mars, and Earth brings us to the true heart of tonight's mystery. Not simply a curious fact about one small strange planet, but a much deeper truth about how temperature actually works across every world in our solar system. A truth that has less to do with distance and far more to do with what happens after sunlight arrives. Let's slow down now and look more closely at the actual physics behind everything we've been describing tonight. Not to complicate the story, but to understand it more completely. Because underneath every comparison we've made, Mercury and Mars, Mercury and Earth, there is a simple, elegant principle of physics quietly governing everything. Every object that absorbs heat eventually releases some of that heat back outward, in the form of invisible radiation. This is true of a sun-baked rock, a warm blanket, even your own body, as you lie here listening to this. Objects radiate heat naturally, constantly, as part of how energy behaves throughout the universe. On a planet with a meaningful atmosphere, much of this outgoing radiation gets intercepted before it can escape completely into space. Gas molecules absorb it, hold onto it briefly, and release it again in random directions, some of it drifting back downward toward the surface, effectively slowing the overall rate of heat loss. Here's the thing most people don't realize. This process, often called the greenhouse effect when discussing Earth specifically, is really just one example of a much broader physical principle. Insulation, in any form, works by interrupting the direct, uninterrupted escape of heat from one place to another. A blanket interrupts heat trying to escape from your body into cold air. A thick atmosphere interrupts heat trying to escape from a planet's surface into the vacuum of space. Remove that interruption entirely, and heat escapes as efficiently, as directly, and as completely as physics allows. Mercury represents something close to a worst-case scenario for heat retention, precisely because it lacks any meaningful atmosphere capable of performing this interruption. When sunlight strikes Mercury's surface during its long daylight hours, that surface absorbs enormous amounts of energy, exactly as we would expect from a planet sitting so remarkably close to the Sun. But once night falls, with no atmosphere present to intercept outgoing radiation, that same surface releases its stored heat directly into space, following an almost perfectly efficient, unobstructed path with nothing standing in its way. Think of it this way. Imagine holding a warm object outdoors on a clear, cloudless night, compared to holding that same object under a thick blanket of clouds. Clouds, much like atmospheric gases on a larger planetary scale, trap some of that outgoing heat and reflect a portion of it back downward. This is why clear nights here on Earth tend to feel noticeably colder than cloudy ones, even when daytime temperatures were identical. Now, imagine removing not just the clouds, but every trace of atmosphere entirely. That is essentially what happens across Mercury's surface every single night, on a scale far more extreme than anything we experience even on our clearest, coldest nights here on Earth. This same fundamental principle explains why the permanently shadowed craters near Mercury's poles reach such extraordinary, almost unbelievable cold. These regions never receive any direct sunlight at all, meaning they never accumulate any stored heat in the first place. And with no atmosphere present anywhere on the planet to circulate warmth from nearby sunlit regions into these shadowed pockets, they remain perpetually isolated from any source of heat whatsoever, drifting ever closer toward the same profound cold found in the empty spaces between stars. And this brings us to something worth pausing on for a moment. The vacuum of space itself has no temperature in the way we normally think about temperature. Space is mostly emptiness, with too few particles present to carry heat the way air or water does here on Earth. But objects sitting within that vacuum, without any source of warmth nearby, gradually radiate away whatever heat they contain, approaching a background temperature only a few degrees above what physicists call absolute zero. This is the fate awaiting anything left long enough in true darkness, far from any star's warming light. Mercury's permanently shadowed craters sit remarkably close to this same profound, universal cold, hidden away just miles from one of the most intensely sunlit surfaces anywhere in our solar system. Understanding this physics helps clarify something important about the nature of temperature across our entire solar system. Heat is not simply delivered and then permanently retained by whatever surface receives it. Heat is constantly attempting to escape, to radiate outward, to spread from warmer regions toward colder ones, following the same basic principles wherever it occurs, whether inside your own home or across the surface of a distant planet. What determines a world's temperature, ultimately, is the ongoing balance between heat arriving and heat escaping, not simply how much initially arrives in the first place. And once you understand this underlying balance, Mercury's strange, contradictory nature stops feeling quite so impossible. It becomes, instead, a clear and vivid demonstration of exactly what happens when a planet receives enormous amounts of solar energy, yet possesses almost nothing capable of holding on to that energy once its source disappears from view. A lesson written not in equations, but in the astonishing contrast between blistering days and frozen, permanently shadowed nights, existing side by side on the very same small spinning world. Let's pause here for a moment. Let's step back from craters and radiation and orbital mechanics and simply sit with what we've uncovered so far tonight. Because underneath all of these details, all of these numbers and comparisons, there is a single, quiet truth waiting to be recognized. When we first began this journey, it felt entirely reasonable to assume that a planet's warmth depends primarily on its distance from the sun. Closer means hotter, farther means colder, simple, predictable, and comforting in its simplicity. But Mercury, this small contradictory world sitting nearest to our star, has spent this entire story quietly dismantling that assumption, piece by piece, revealing something far more nuanced hiding underneath. Here's the thing most people don't realize, and perhaps the most important idea in this entire story. The sun provides energy. That much is straightforward and undeniable. But what happens to that energy once it arrives depends entirely on the world receiving it. Some planets hold on to that warmth carefully, wrapping it in thick, insulating atmospheres that allow heat to linger long after sunlight fades. Other planets, like Mercury, receive that same energy and simply cannot keep it, watching it escape almost as quickly as it arrived, radiating back out into the emptiness of space with almost nothing standing in its way. Think about how differently this reframes everything we've explored tonight. Mercury is not colder at night despite being close to the sun, as though its proximity should have protected it from such extremes. It is colder specifically because of how little it has to work with, atmospherically speaking, regardless of how much raw sunlight it receives during the day. The sun's warmth arrives faithfully, intensely, exactly as its closeness would suggest, but that warmth passes through Mercury almost like light through an open window, rather than settling in like heat trapped within a well-insulated room. This idea extends far beyond just one small cratered planet. It applies quietly and consistently across our entire solar system, and likely across countless other worlds orbiting distant stars that we may never have the chance to study directly. A planet's true climate, its capacity to remain warm, stable, and hospitable, depends on far more than simple proximity to its star. It depends on atmosphere, on chemistry, on rotation, geography, and countless subtle factors working together in ways that distance alone could never fully predict or explain. And there is something quietly humbling in recognizing this truth. It would be simpler, in some ways, if the universe operated purely on straightforward, predictable rules. Closer to a star always means hotter. Farther away always means colder. No exceptions, no contradictions, no need to look any deeper than a single number representing orbital distance. But the universe rarely offers such simple comfort. Instead, it rewards patience, curiosity, and a willingness to look beyond the most obvious explanation towards something more complete, more nuanced, and ultimately more interesting. Mercury teaches this lesson perhaps more vividly than almost any other planet in our solar system, a world capable of melting lead under direct sunlight, and capable, within the very same rotation, of temperatures that rival the coldest depths of interstellar space. Not because it defies the laws of physics, but because it reveals just how many variables truly influence a planet's relationship with heat, once you take the time to look closely enough. This realization also carries a quiet echo back toward our own experience, here on Earth, in this moment, as you listen to these words in the dark. We often assume comfort and stability are simple, guaranteed conditions, requiring little thought or appreciation. Yet everything gentle and livable about our own nights depends on an intricate, delicate balance of atmospheric chemistry, distance, and countless other factors working together in quiet harmony. Mercury, in its extremity, helps us appreciate just how remarkable and how easily disrupted that balance truly is. As we move forward now toward the final chapters of tonight's story, we carry this understanding with us. Mercury's contradictions are no longer confusing or difficult to explain. They have become instead a lens through which we can view the entire solar system more clearly. A reminder that the universe rarely reveals its deepest truths through simple, single explanations, but instead through patient observation, careful comparison, and a willingness to sit with complexity until it gently reveals its own quiet logic. Let's try now to hold the whole picture of Mercury in your mind at once. Not piece by piece, the way we've built it tonight, but as a single, complete portrait of a world unlike almost anything else orbiting our sun. A planet defined not by one extreme, but by two existing together, inseparable from one another, shaping everything about what this small world truly is. Picture Mercury as it actually exists, spinning slowly through space, carrying its blazing hemisphere and its frozen hemisphere together as a single, continuous surface. There is no true separation between these two conditions. No wall, no boundary marked by anything other than the slow, patient turning of the planet itself. The same ground that once melted, lead beneath a merciless sun will, months later, on the very same patch of surface, sit locked in cold, approaching the depths of interstellar space. Two entirely different worlds, somehow contained within one. Here's the thing most people don't realize. This is not simply a planet that happens to have a hot side and a cold side, the way you might imagine two rooms in the same house set to different temperatures. It is a planet whose entire identity is built around this contrast, this violent oscillation between conditions that would, each individually, be considered among the most extreme found anywhere in our solar system. Mercury does not compromise between hot and cold. It fully commits to both, one after another, in a rhythm stretching across nearly 6 Earth months for a single complete cycle. Think about what it would mean to actually stand somewhere on Mercury's surface as this transition unfolds. Not at the boundary between day and night, which we will explore shortly, but simply existing through an entire cycle in one place. Months of blistering, merciless heat, intense enough to reshape any assumptions you might carry about warmth and survival, followed by months of profound, absolute cold, deep enough to freeze away any lingering trace of that earlier heat completely. No spring, no autumn, no gentle transition easing you from one extreme toward the other. Just two total, complete conditions, taking turns governing the same patch of ancient, cratered ground. And we must not forget those permanently shadowed regions we uncovered earlier, hidden within Mercury's polar craters, existing entirely outside this rhythm altogether. While most of the planet swings between its two great extremes, these small ancient pockets remain locked in a single, unchanging condition, colder than almost anywhere else in the solar system, forever untouched by the blazing heat defining the rest of this world. Mercury, then, is not simply a planet of two extremes. It is a planet capable of holding three distinct realities simultaneously: blazing heat, plunging cold, and permanent, ancient darkness, all coexisting within the boundaries of a single, small sphere. This complexity is precisely what makes Mercury such a compelling subject for study and such a powerful lesson about the true nature of planetary temperature. It would be far simpler, far easier to summarize if Mercury was simply hot given its proximity to the Sun, or simply cold given some other straightforward explanation. Instead, Mercury insists on complexity. It refuses to be reduced to a single number, a single description, a single simple story. It demands that we understand geography, rotation, atmosphere, and shadow together as an interconnected system rather than isolated facts. And perhaps this is the deeper lesson Mercury offers us tonight. Beyond simply explaining why it runs colder than planets, twice as far from the Sun, extremity itself is rarely simple. The most dramatic contrasts in nature, whether found on a planet's surface or in circumstances closer to our own lives, tend to emerge not from a single cause but from the interaction of many factors working together, sometimes reinforcing one another, sometimes creating contradictions that only reveal their logic upon closer, more patient examination. As we continue moving through tonight's story, carrying this fuller understanding of Mercury's dual, sometimes triple nature, we prepare now to look at how humanity actually came to know all of this. Because everything we've discussed so far, the melting heat, the plunging cold, the ancient ice hidden in permanent shadow, did not arrive to us through guesswork or assumption. It arrived through decades of careful observation, daring engineering, and spacecraft brave enough to approach this small, extreme world closely enough to finally reveal its true, complicated nature. Long before any spacecraft ever approached Mercury, this small planet remained one of the most difficult worlds in our solar system to study closely. Its proximity to the Sun, the very quality that makes it so scientifically fascinating, also makes it remarkably dangerous and difficult to reach. Any spacecraft travelling toward Mercury must contend with the Sun's powerful gravity, constantly pulling it inward, along with intense heat and radiation, far greater than anything experienced by missions travelling to more distant planets like Mars or Jupiter. The first spacecraft to ever visit Mercury was named Mariner 10, launched in the early 1970s. Rather than travelling directly toward Mercury, engineers designed a careful, indirect path using the gravity of Venus to bend the spacecraft's trajectory and slow its approach enough to eventually reach Mercury safely. This technique, now commonly used throughout space exploration, allowed Mariner 10 to fly past Mercury 3 separate times, capturing the first detailed images humanity had ever seen of this small cratered world up close. Here's the thing most people don't realize. Because of the specific timing and geometry of these flybys, Mariner 10 only ever photographed roughly half of Mercury's surface, leaving the other half completely unseen and unmapped for decades afterward. For years, scientists possessed detailed knowledge of only one hemisphere of this planet, while the remainder stayed hidden, a genuine unexplored frontier sitting right there in our own solar system, closer to us than nearly any other unexplored world remaining. It would take more than 30 years before another spacecraft finally returned to complete our understanding of this small, mysterious planet. That spacecraft, named Messenger, launched in 2004, embarking on an extraordinarily long, carefully engineered journey that required multiple gravity-assisted flybys of Earth, Venus, and Mercury itself, before finally settling into a stable orbit around the planet in 2011. This journey alone took nearly 7 years to complete, a testament to just how difficult and delicate it truly is to safely approach a world sitting so close to the Sun's powerful gravitational influence. Once safely in orbit, Messenger spent 4 years systematically mapping Mercury's entire surface for the very first time, finally completing the picture that Mariner 10 had only partially begun decades earlier. Beyond simply capturing images, Messenger carried instruments capable of measuring surface composition, mapping subtle variations in Mercury's magnetic field, and detecting the presence of specific elements hidden within the planet's thin exosphere and its permanently shadowed polar craters. This mission fundamentally transformed our understanding of Mercury, revealing details that ground-based observation and brief flybys alone could never have uncovered. Engineering a spacecraft capable of surviving this environment required extraordinary care and innovation. Messenger's design included a specialized sunshade, a large, heat-resistant shield positioned to protect the spacecraft's more delicate instruments from Mercury's intense solar radiation, allowing sensitive equipment to remain at safe operating temperatures despite operating so close to the Sun. Without this careful engineering, the extreme conditions we've spent this entire story exploring would have made sustained scientific observation completely impossible. Today, a new mission continues this legacy of careful, patient exploration. A joint effort between European and Japanese space agencies, named Bepi Colombo, launched in 2018, is currently making its own long, gravity-assisted journey toward Mercury, following a path similarly bent and slowed by multiple flybys of Earth, Venus, and Mercury itself. Once it arrives and settles into orbit, this mission promises to build even further upon everything Mariner 10 and Messenger first revealed, examining Mercury's surface, its subtle magnetic field, and its strange contradictory temperature, extremes with even greater precision than ever before. Every detail we've explored tonight, the melting daytime heat, the plunging nighttime cold, the ancient ice hidden within permanent shadow, exists in our understanding today because of missions like these. Spacecraft engineered with extraordinary care, launched on carefully calculated trajectories spanning years of travel, all in pursuit of understanding a single small contradictory planet sitting closest to our Sun. It is a quiet reminder of how much patient curiosity and how much careful human ingenuity stands behind even a single fact about a distant world. And it is precisely this hard-won understanding that allows us now to imagine something almost impossible to picture directly. What it might actually feel like to stand somewhere on Mercury's surface, exactly at that fragile, fleeting boundary between its blazing daylight and its frozen, endless night. Close your eyes for a moment, if they are not already closed. Let's walk together toward a place that exists only in imagination, because no human being has ever stood there and likely never will. A place at the very edge between Mercury's blazing day and its endless, frozen night. The Terminator, scientists call it. The thin, shifting lines separating light from darkness. Imagine standing at that exact boundary, one foot resting in the last dying light of an 88-day-long afternoon, the other foot already sinking into shadow. Behind you, the ground still radiates heat absorbed across months of relentless sunlight, warmth pressing upward through whatever might be standing there. Ahead of you, in the direction of that advancing darkness, the temperature has already begun its steep dramatic fall, the first whispers of a cold that will eventually rival the depths of space itself. There is no wind here to carry sound across this landscape, because there is no air at all to carry anything. If you dropped a stone onto the ground beside you, you would see it fall silently, without even the faintest whisper of impact reaching your ears. Complete silence, not the peaceful quiet of a sleeping house, or the gentle hush of falling snow. A deeper silence, an absolute one. The silence of a world with nothing to carry sound at all, stretching in every direction, beneath a sky holding both blazing sun and countless unblinking stars at the very same moment. Here's the thing most people don't realize when they try to imagine standing somewhere like this. The sky above you would show no gradual transition either, no twilight colors spreading gently outward the way we see here on Earth just before sunset. Only the sun itself, hanging enormous and blinding near the horizon, surrounded by a sky as black and star-filled as midnight, because there is no atmosphere present to scatter light into anything resembling dusk. Daylight and midnight existing together, side by side, in the very same glance upward. Look down at the ground beneath you, ancient and cratered, scarred by billions of years of impacts from asteroids and comets, with almost nothing to erode or soften those markings across time. No wind to smooth these edges, no rain to wear down these craters, no shifting continents to reshape this landscape the way they slowly do on Earth. Whatever shape this ground held a billion years ago, it very likely still holds today, patient and unchanging, indifferent to the extraordinary temperature swings passing endlessly across its surface. And now, imagine simply waiting there, at that boundary, as Mercury's slow rotation gradually carries you deeper into darkness. The warmth beneath your feet, accumulated across nearly 3 Earth months of relentless sunlight, would begin fading almost immediately once true night arrived. Not gradually, the way an evening cools here on Earth, but steadily, relentlessly, hour after hour, as stored heat radiates directly outward into space, with nothing at all to slow its escape. Within a surprisingly short span of time, conditions around you would already be plunging toward extremes far beyond anything survivable. This image, strange and almost dreamlike as it may feel, captures something true and important about Mercury's nature. It is a world without gentle transitions, without soft mornings or comfortable evenings easing one condition into another. Just this narrow, fleeting boundary existing for only a brief moment before giving way entirely to one extreme or the other. Blazing heat behind, deepening cold ahead, and complete, unbroken silence stretching endlessly in every direction. There is something quietly humbling about imagining this place, a reminder of just how rare, just how fragile, the gentle balance of our own world truly is. The soft transitions we experience here on Earth, sunrise easing gradually into daylight, evening fading gently into night, exist because of an atmosphere working constantly, invisibly, to smooth out the extremes that would otherwise define our own planet's relationship with the Sun. Mercury has no such gift, only sharp immediate boundaries, separating fire from ice, light from permanent shadow, sound from absolute, unbroken silence. As we prepare now to close tonight's journey, let this quiet image linger with you for a moment longer. That thin, fragile boundary, that perfect, complete silence. A reminder of just how strange, how extreme, and how quietly beautiful our solar system truly is, even in its harshest, most unforgiving corners. As we come to the final part of tonight's journey, let's step back one last time, away from craters and shadows, away from spacecraft and radar signatures, away from the strange, silent boundary between light and dark. Let's simply sit for a moment with everything Mercury has quietly taught us tonight. We began with a contradiction, a planet closest to the Sun, and yet, in certain places, colder than worlds sitting 2 or 3 times farther away. It felt at first like a simple curiosity, an unusual fact about a small distant world most of us rarely think about. But as we've moved through this story together, that curiosity has grown into something larger, a deeper understanding of what truly determines warmth, comfort, and stability, not just on Mercury, but across every world capable of orbiting a star. Here's the thing most people don't realize until they've heard a story like this one in full. Warmth is never guaranteed simply by closeness. Comfort is never guaranteed simply by proximity to a source of light and energy. It depends on balance, on atmosphere, on the quiet, invisible mechanisms working constantly to hold heat in place, rather than allowing it to escape instantly back into the emptiness of space. Mercury lacks this balance almost entirely, and its surface reflects that absence in the most extreme, most vivid way imaginable. And this brings us gently back home, back to Earth and to the atmosphere surrounding you right now, even as you lie here listening in the quiet dark. That thin, fragile layer of gas, so easy to overlook, so rarely appreciated, is the single reason your nights feel gentle rather than catastrophic. It is the reason oceans remain liquid rather than freezing solid. It is the reason life itself became possible here, flourishing across billions of years, protected by something most of us never even think to thank. Think about how rare this balance truly is. Among all the planets we've discussed tonight, Mercury's extremes, Mars's thin, insufficient atmosphere, Venus's runaway heat trapped beneath thick, suffocating clouds, Earth stands apart. Not because it sits at some perfectly average distance from the Sun, but because it holds precisely the right atmosphere, precisely the right chemistry, precisely the right conditions to remain gentle, stable, and alive. A narrow, precious exception, surrounded by worlds defined by extremes we could never survive. We are, each of us, standing on a planet that got the balance right. Not through any guarantee written into the nature of the universe itself, but through an extraordinary, almost improbable combination of circumstances, unfolding across billions of years. Mercury reminds us of this by embodying its opposite, a world that received enormous warmth from the very same sun that warms us gently each day, yet lacks the simple, quiet gift of an atmosphere capable of holding on to that warmth once night falls. And perhaps this is the quiet, comforting truth to carry with you as tonight's story comes to a close. We often search the universe for wonder, for extremes, for mysteries capable of humbling our sense of scale. Mercury certainly offers all of that. Fire and ice existing together on a single small world, spinning patiently around the same star that gives us our own gentle days and nights. But in searching outward towards strange, distant worlds like this one, we sometimes discover something quieter, something closer to home, an appreciation for the very ordinary, very familiar balance we so easily take for granted here on Earth. We are, in some very real sense, the universe noticing itself. Small collections of atoms, once scattered across ancient stars long since gone dark, now gathered together, curious enough, patient enough, to build spacecraft capable of crossing millions of miles just to understand why one small planet runs so strangely hot and so strangely cold. That curiosity, that quiet desire to understand, is itself something remarkable, something worth appreciating as much as any distant, icy crater or blazing sunlit plain. Thank you for joining me tonight, for staying with me through the heat and the cold, through the silence and the shadows, through fire and ice existing side by side on the same small contradictory world. If tonight's journey brought you any sense of wonder, or any quiet comfort as you drift towards sleep, consider leaving a like or subscribing, so this small corner of curiosity can continue reaching other quiet minds like yours. And the next time you find yourself outside on a clear, calm night, looking up at that familiar scattering of stars above you, remember this. Somewhere out there, closest of all to our sun, a small world spins quietly through its own extraordinary contrasts, teaching us without ever knowing it just how remarkable our own gentle, balanced place in this universe truly is. Sleep well tonight. Keep looking up at the stars. Good night.